about what type of stick you are wearing, etc. So it changes. So that's okay. Today's first session, we have two speakers, Dr. Kitheri Joseph, who is an associate professor, and Dr. Sehila Gonzalez, global director of Fusion. So she is from, both are, I think, online. Oh, how nice. I'm very happy that you are here. So you are, did I pronounce your name correctly? Uh, one who will teach us how we take the nuclear fuel from lightweight reactor to fast reactor. When I was working in BRC, that time we had all lightweight reactors and fast reactor was being built in Kalpakam. So now that is the next step you are going ahead. And let me read a little bit of your biodata. Your metal fuels recycle group, materials chemistry and metal fuel recycle group here, and Indira Gandhi Center for Atomic Research, IGCAR Kalpakam. Somehow we think IGCAR is an extension of BRC. So you did bachelor's degree from Auxilium College, Katpadi, and you were the topper and university rank holder. Congratulations, my dear girl. Master's degree from Loyola, Chennai, you are a gold medalist. Wow, so always a topper throughout. And BRC Training School 33rd batch of chemistry joined in 1989. So I am from 12th batch, so most probably I might have taught you Fortran, I don't remember, or not. Normally it was a routine for me to teach Fortran to all training school youngsters, so that's okay. Then you joined IGCAR in 1990 and gained experience in the field of sodium chemistry, electrochemical hydrogen meter, thermal analysis, solid state nuclear materials, and nuclear waste management involving iron phosphate glass. Presently, you are the Associate Director, Metal Fuel and Reprocessing Group. Once again, congratulations for that, because being Associate Director is a no mean feat in a man's world. Now, is it a man's world or is it going to be women and man's world together? That change has to be there. When we were there, it was totally men's world, and somewhere we were hiding here and there, and they were trying to be very gallant to us. I remember, don't walk too fast, Mrs. Mahajan. We have to open the door for you. Arey, what is this? I can open the door myself. It used to be like that, but I'm so happy that now it has become a equal men and women. You are leading a team from IGCAR in Indo-UK civil collaboration in the field of nuclear waste management. That's very good. So now I feel that you give us the experience of your research. And I think after that, I will, Vijaya, you are coming and sitting here, no? Anyway, so we'll see then. I'll talk about Sehila after she finishes her talk. You will get 15 minutes for your presenting your talk, and then 5 minutes for question answers. Okay, please. You come here because I don't have a.
Good morning, one and all. Thank you, ma'am, for your kind introduction. I understand that you are from 12th batch and we are from 33rd batch, and I see a representation from first batch onwards. Ma'am is in front of me. And the topic of my interest is metal fuel, pyro reprocessing, waste management, I'm going to give only a very brief perspective. The overview of my topic is like a very basic concept, then what we do in the metal fuel fabrication and lab scale pyroprocessing. You go for engineering scale pyroprocessing and a small R&D on nuclear waste management. And before I go to the next topic, I just want to tell you about Kalpakam. Kalpakam is a place where you have Harmini, which is Kalpakam mini reactor, which consists of uranium-233, only reactor which uses uranium-233 even internationally. And we have MAPS, which is representatives are here. And we have FBTR, which is fast breeder test reactor, and PFBR, which is under process. So you can see from light water to fast reactor, as ma'am mentioned in the introduction. A few basic concepts which you all know, that fission through which we get the energy. I'm not going into the details of that, but I just like to tell you, since we are interested in breeder reactors, that is fast reactors, the first experimental breeder reactor EBR1 was constructed in December 20, 1951 to power 200 watts light bulbs. That is the actual history. You can see now where we are now, we know. And the first reactor as such is Chicago Pele, which is in 1942. And I go into my topic straight away. As you all, I've informed you that we are interested in metal fuel. What are the advantages of metal fuel? Heavy metal atom density, high thermal conductivity, breeding ratio is higher than oxide fuel, lowering of doubling time, easily fabricated, and it can be with a close dimensional tolerance. And we go for non-aqueous reprocessing, compatibility with metal coolant, which is sodium, and above all, it is highly incurrently safe. And now we're going to the metal fuel fabrication, which we do in our group. Actually, our objective is develop the technology, the fabrication technology for fuel slugs, gain experience by fabricating blanket slug. What I mean is uranium 6 weight % zirconium. Then experience in fabricating the metal fuel pin, which corresponds to 531.5 mm length. And finally, test irradiation of metallic fuel in FBTR. Presently, we received the fuel slug UPUZR from BAR. We made the metal fuel pin, and there are variety of techniques you have for casting methodology, but the IGCAR, Indira Gandhi Center for Atomic Research, uses injection casting system. What do you mean by injection casting system? You just imagine yourself having a cup of soup or something, or a juice. You're trying to pull through the straw. That's the basic methodology you can think of. But the entire process is happening at very high temperature under closed environmental condition. That is, you have two chambers, which the first chamber consists of all your mold. Bottom chamber is graphite crucible coated with yttria to hold all your uranium, zirconium metals to be melted. And so you require temperature, vacuum, pressure ports, and control measurement systems. The top chamber, which consists of the capillary, what we talk about the capillary, which will be maintained at 550 degrees centigrade, and this will be inserted into the molten alloy. That molten alloy is kept at 1450 degrees centigrade. You can imagine the entire process is happening at 1450 degrees centigrade, and the entire thing, IC equipment, injection casting equipment, is housed inside the glove box, and all the control system, panel, everything is outside the glove box. So the process consists of like this: yttria coated graphite crucible. So you know yttria is the stablest oxide which will not interact with uranium, plutonium, and zirconium. So you coat it with yttria. That has a technology again. Then you have a quartz tube which will be inserted at 1450 degree. that internal, that means 6 mm dia should be coated with quartz, yttrium. All the process have been done inside in our IG car only. The entire process, finally, you pressurize the injection chamber, you allow the melt to raise inside quartz tube, and then you cut open to get the slug. The moment you are getting the slug, that means you have to go for quality check. What are the things? You have metal feed, injection melting, demolding, characterization. You should have physical, chemical, as well as metallurgical. The moment it is not qualified, you recover the metal, do the casting. If it is qualified, put it in T9 clad tube, sodium extrusion, slug loading, N-plug welding, sodium bonding. Fuel pin is characterized again. Accepted fuel pin goes for assembly. As you all know, uranium cleaned one I have shown here. The slug which is casted, uranium zirconium slug, is also shown here. And the non-metallic impurities, when we say oxygen should be less than 85 ppm, actual spec is less than 100 ppm, and carbon need to be less than 5000 ppm as per the specification, but what we get is less than 1000 ppm of carbon. And as I told you, we need to go for all the characterization, XRD to check whether it is UZR, U68% ZR, metallurgical characterization to check, and the dimensions, the surface, everything has been checked, mapping the distribution of uranium and zirconium to prove that it is uniform. In addition to that, we do chemical analysis of the ensured material. The uncertainty in uranium is around 0.2%. The uncertainty in zirconium is around 0.1%. And next, we show the entire system. The 1 kg injection casting, all the trial runs are used using copper. And we have one more 10 kg system also. Sodium wire extrusion, sodium bonding. You have slug retrieval facility. The characterization lab for the non-metallic impurities. Cutting and polishing machine for inside the glove box, everything. Then you can see the molten alloy, how it looks at 1450 degrees centigrade, and all the system need to be under high purity argon. So you require argon recirculation and purification system. The ppm level of oxygen need to be less than 20 ppm. And this inert atmospheric glove train has been already dedicated to nation by Honorable President of India, the former President Govind, and 1 kg injection casting system and all the allied facilities. Actually, we received the PUZR slugs from BAR. We made UZR blanket slugs. They are under irradiation, under FBTR. The next topic is on the pyrochemical processing, lab scale and engineering scale, where this is a non-aqueous process. The word tells you through electrochemistry, so electro refining. So the fission products containing the spent fuel is taken in the anode basket, and that is taken in the anode basket, and depending on the chloride stability. The lithium chloride, potassium chloride, you take it along with uranium chloride is taken as an electrolyte, which is present here. And you have solid cathode as well as liquid cadmium cathode. Through electrochemistry, by playing with the potential, you can deposit uranium in the solid cathode. The remaining uranium, plutonium, and all the minor actinides can be electrochemically deposited in liquid cadmium cathode, and that can be removed. As I told you, the highest stability of alkaline and alkali earth chlorides will remain in the molten salt. Minor actinides and plutonium, which are electro-transportable, are taken into the cadmium cathode, which can be recovered. And the plutonium and along with minor actinide is taken. Uranium alone, by controlling the potential, you can deposit at the solid cathode, which is shown as a blue material there. And the noble metals remains as noble metals in the anode basket, which can be recovered. And this tells about, normally we take two double model go box. This particular system, you can imagine it is with 26 meter cube containment box, which has all the facility to handle highly sensitive molten salt, which is moisture sensitive, and you are able to deposit uranium, recover uranium, induction melt it, and make it to uranium alloys. The next is the engineering scale. I was talking to you about double module go box. Then I was talking to you about 26 meter cube boxes. The present system, the engineering scale facility is with one of its kind in our country, which corresponds to 500 meter cube containment box. People who visit IGCAR, please check this facility also. This has 500 meter cube containment box. You have to have a stringent environmental condition. The oxygen level and the moisture level need to be less than 50 ppm. You can imagine. And all the facilities has to be remotely handled. So we would like to have that experience before going into hot cell. So we had gone for this construction where all the electro refining station, electrodes attaching, detaching station, scrapping facility, and tilting of uranium with salt, and automated vacuum and distillation facility to distill the salt as well as melt the uranium. And which you can see, this is the containment box which consists of the entire unit, which is 500 and we have prepared 1 ton salt of lithium chloride, potassium chloride, which you can imagine with the stringent purity. And this is through 10 kg level of pyroprocessing with remote handling experience. And before start with uranium, we always do with cathode deposition by copper. You melt it, you form the copper blocks, and you can see the fresh cathode which is shown here, and cathode with uranium deposit, uranium deposited in the cadmium pool. All the things have been consolidated. And the next on the R&D, another 5 minutes I'll be able to. Yes. And on nuclear waste management, and you all know, BRC works for light water reactors, and IGCAR, our center is towards applied oriented work towards fast reactor management. So why we are interested only in high level waste? So high level waste means you have to store it in a solid form. The solid form can be ceramic, glass ceramic, or a composite. And why we go for vitrification, which is glassification rather, that is because of the industrial process. And the literature industrially highly viable. You have to take care of the durability, chemical, mechanical, and thermal and radiation stability. You should have a lower liquidus temperature so that you take minimum time for homogenization, better waste loading, accommodation of all the composition required. With respect to fast reactor waste, where cesium and molybdenum content is very, very high, borosilicate glass is not the suitable matrix because it can take maximum of 2.58% only. But whereas iron phosphate glass, which is an alternate matrix, can take 1 order higher. 25% of this can be taken, and the salient features are shown here. There are certain ways which can be loaded even up to 58%, and the number of glass formers and modifiers are very, very limited. Although all phosphate glasses are corrosive, an exception is iron phosphate glass, and commercially feasible with the normal joule melters. And these type of works have been done on an R&D scale. All the characterization with respect to thermophysical, forming ability, glass stability, and this itself is one typical topic which can go for 1 hour. But what we would like to tell you, why this Indo-UK program started, because we were able to give an iron phosphate glass with less than 1% of iron 2+ concentration, which is internationally they could not do it. They could only complete up to 17% of iron 2+, whereas we achieved through a soft chemical route to get 99% iron phosphate glass with iron 3 ion. And this shows you the iron phosphate glass, which is molten and formed as a solid form at the 1 kg level. And this is our team. And this team consists of we have 3 divisions, and the 3 divisions takes care of metal fuel fabrication, and then pyroprocessing at the lab scale, pyroprocessing at the engineering scale. My sincere thanks to Director Ajikar, Director FCM of CG, and the IFSA organizers and IFSA team who are present here, and to the IFSA Kalpakkam chapter. I would like to conclude my saying, I am a member of a team and I rely on the team. I defer to it and sacrifice for it because the team, not the individual, is the ultimate champion. Thank you. Yes, ma'am. Ma'am, actually, my teacher who's here, Shyamla ma'am, already told me, cut short, you have to complete in time. Yes, ma'am.
Hello. Not good. Hello. So Meera wants, I think.
Very nice presentation. Congratulations on your achievements and illustrious career. My question is, there are few, but I will ask only one. Maybe I'll ask the rest later. See, you must have heard this term wealth from waste, ordinarily and particularly in nuclear reprocessing. So when you mentioned about molybdenum, cesium, etc., in the high-level waste, have you thought of separating them? Because you already have separated uranium, plutonium, etc., to make it into like what they have made in pencils for blood irradiation. That's one. But if you can separate short-lived molybdenum or iodine, it has a great use and you will have gotten rid of the activity also. Has anything been done on that?
Yes, ma'am. Actually, I would like to thank ma'am for this wonderful question, because we do iodine trap studies in our department, where right now, chemistry-wise, whether it is radioactive material or a stable element, it is not going to change. So we have done using zeolite, silver impregnated zeolite for sorption of iodine and xenon. We have already completed. As you pointed out very clearly, we are already on the process of separation of cesium, where cesium-137 in the form of a glass is used not only in the medical field, it is also used for the sludge treatment and industrial purpose. And I can proudly say iron phosphate glass, which I was talking to you about, that has less than 0.5 weight% of loss of cesium when you are making the glass compared to borosilicate glass, and you can load maximum of 30 weight% of cesium, which is difficult in borosilicate glass. We are in the process, and we are in the R&D level, not to the level of loading cesium-137, but I will promise you, we'll soon reach to that level.
Congratulations, but I would like you to coordinate with BRIT. As you said, it's a team within, but team also within DA.
Yes,
I wish you all the best.
Thank you.
Good morning, ma'am. I'm Karthikani from Karp Kalpakkam. I have few questions. First is, can we use pyro reprocessing for reprocessing metallic oxide fuels like UO2 oxide fuel? If we cannot use, then why?
I'll tell you, we can use, but we have to introduce one small step in between. Very simple. Metal oxide need to be converted to metal. Then it can be used for pyroprocessing. Okay. But that is possible. We have done R&D on that. We had taken uranium oxide by direct electrochemical reduction method. We have reduced uranium oxide to uranium, which I am not presenting here. We have done that uranium change, and that uranium, after vacuum melted, it is used for casting your UZR alloy. That is possible, but you have to introduce a step in between, because what is your interest is more important. Are you interested in metal fuel? Then you will straight away go for metal fuel fabrication. Are you interested in conversion of existing MOX to your metal fuel? Then you can introduce a step in between called direct electrochemical reduction. direct oxide electrochemical reaction, which is called as DOER. That step you have to introduce in between, convert to alloy, and then you can go ahead with reprocess.
Ma'am, I have one more question. This U233 material we are using in Kamini, no, where it is getting fabricated, is it also in from your
From
division?
bark, BS.
Okay, ma'am. Thanks.
Let me congratulate Kalpakam team, means your team, for reducing iron 2+ content in the iron phosphate to a great extent, means it's a real great achievement. But I would like to know, is this the only problem with iron phosphate class, or is there any other problem to be still solved so that, you can easily use this glass for your waste management systems? Yeah, it's my curiosity question to know that reducing iron 2+ content alone is enough, or anything more is to be done.
Ma'am, I tell you why I am interested in iron 3+. Actually, iron 2+ in the glass matrix acts like glass modifier. That means it depolymerizes the glass structure. Whereas iron 3+ acts like a glass intermediate. When it acts like a glass intermediate, it tries to have more polymerization, shorter bond length with iron and oxygen. Fe3+ with oxygen is shorter compared to iron 2+ and oxygen. All chemists knows that. That helps in polymerization. So you would like to have more of iron 3+, but the lab scale preparation, madam, all this, normally they will not take phosphorus pentoxide for their preparation. They will prepare in situ P2O5 by decomposing ammonium dihydrogen phosphate. But then when you do that, ammonia is getting liberated. When you do get ammonia getting liberated, it acts like a reducing agent for during your preparation. That reduces your iron 3 to iron 2+. So we did not follow that technique. We prepared a crystalline matrix, which is Fe4P2O7 thrice, which is nothing but pyrophosphate of iron 3+. That we have melted, quenched, and formed this IPG, where there is no formation of ammonia or hydrogen atmosphere during preparation, which does not reduce your iron 3+ to iron 2+. So we could successfully get iron 3+ maximum level.
Any more questions? Thank you, ma'am, for the
Thank
nice
you.
program,
Thank you.
nice
Thank you.
explanation. Our next speaker, Gonzalez, is already there online. We welcome her.
Welcome, Dr. Sehila Gonzalez. And I should say good evening to you and
Well,
good morning to all of us. So I think you are speaking from Boston, means it must be evening there.
it's 1 a.m.
Sehila
or
Gonzalez
what? 10 to
Boston.
1 a.m.
in material science, material physics from University of Complutense de Madrid, Spain, and an MBA by the EOI Business School as well. She has 20 years of experience in fusion technologies and materials. She is currently the Global Director of the Fusion Energy Program at Clean Air Task Force. Previously, she was working at International Atomic Energy Agency as nuclear fusion physicist for more than 8 years. Before joining IAEA, she was responsible officer for Fusion Material Development Program at EFDA, that is European Fusion Development Agreement, Eurofusion, in Garcin-Bell, München, Germany. In addition, she was appointed European Technical Coordinator of the International Fusion Energy Research Center, IFERC project between Europe and Japan, as well as the member of Karlsruhe Institute of Technology Scientific Advisory Board in the research field of energy. She has been the chair on the 9th annual assessment of fusion of energy and member of the review committee for the European spallation source re-baseline review. She is also the chair of the Women in Fusion group. Currently, she is the Global Director Fusion Program, Clean Air Task Force, Boston. So quite an impressive CV, and you are keen on fusion. So fusion, you will tell us why fusion is better than nuclear fission as a fuel. Normally, all of us are used to fusion. We do get our warmth from sun. I think sun's energy is a nuclear fusion. Am I right, Meera? So we are used to that, but please tell us more about your fusion and how you have made it into a clean environmental direct. Over to you, madam.
Thank you very much. Can you hear me? Hello, can you hear me?
Yes, we
ma'am.
can hear you.
Okay, fine. I'm going to share my presentation right now. Yes. Can you see the presentation?
Hello.
Hello,
Please, we can hear you and please carry on.
okay, sure, fine. So, just please, could you confirm that you can see my presentation?
Hello, ma'am, make into presentation.
Please start and go in
Okay,
presentation mode because we can see only a headline.
okay, I went to presentation mode. I will,
You have to share your PPT.
yeah. Mhm.
Would you like to help?
I think now, can you see?
Yeah, it is okay. Now you have to talk for 15 minutes for your presentation and 5 minutes for question answers.
Great, excellent. Thank you very much. I would like to first to start the talk thanking the organizers of this event to introduce fusion and to invite me. So it's always good to be part of this kind of events where fusion and other energies can be discussed. So the title of my talk is Fusion, an attractive zero carbon source of energy. And you will see over the presentation why this is a zero carbon source of energy and which are the main features of this new type of energy. Okay, this is the outline, which are the merits of fusion, the physical principles of fusion, which are the main difference between fusion and fission, how fusion is produced, which are the different concepts that we have right now, what is going on beyond ITER, which are these new private enterprises emerging around fusion. I would like to say a few words about a global group called Women in Fusion and the final conclusion. So which are the merits of fusion? Why fusion is becoming now popular, which is interesting. The first thing is a carbon-free zero gas emission. We don't produce CO2. It's a completely carbon-free type of energy. It's virtually clean. Fusion don't produce any waste by itself. The outcome of the deuterium-tritium reaction, which is the most popular, is helium and some neutrons, and the helium is completely neutral. And the neutrons are captured within the machine and they are needed to breathe their own fuel. So virtually it's a clean energy. We have low-level manageable waste. It's no long-life radioactive waste production. Is as mentioned by the previous speaker, in fusion you have high-level waste. In fusion we don't have that kind of waste. It's all low-level waste. It's inherently safe. There is no chain reaction. As I will show you later, the difficult thing in fusion is to keep the reaction going. At the moment that you don't reach certain demanding condition, the machine stops. So there is no chance to have any chain reaction or any reaction out of any control. It's virtually unlimited fuel. Why? Because the fuel is deuterium and tritium, and these are isotope of hydrogen. So there is no particular geographical distribution or limitation on that. And it's a reliable source of energy. Fusion doesn't depend on the wind, on the day or the night. It's intrinsically reliable source of energy, day and night, wind or not wind, and whatever temperature, etc. So all these characteristics make the development of fusion really attractive. And in particular, now that we have to fight against climate change and new source of energy are needed because more population are demanding more energy. So which are the physical principles? The physical principle is, okay, we have a reaction of two light atoms, nucleus, that combine to have a heavier one. So usually you have the easiest fusion reaction to do on Earth, and this is why I would say 90% of the concepts are based on that, is deuterium and tritium. So the whole thing is to join these two nucleus to have a heavier one, helium, and to produce a neutron. Is this reaction proven? Is this process happening? Yes, it is. It's the process that takes place in the stars. And is in the 20s of the last century, it was proposed that the mechanism to power the stars was fusion, and this fusion was done within a plasma. So probably you are familiar with the meaning of plasma. Plasma is an ionized gas, which you need to put it at high temperature to be able to have this fusion reaction. So in the sun, you have a really high temperature where all particles, positive and negative, are a certain pressure, so with certain density for enough time to be able to have this fusion reaction. So fusion and plasma is something that goes together. You need a plasma to be able to facilitate, to make possible the fusion reaction, but it's not the only condition, as I will show you later. So we have now understood that fusion is the joining of two light atoms. Deuterium and tritium is the easiest one, and you have helium and a neutron with certain high energy, 14 MeV neutrons. And fission is where you have a large nucleus that break up into small ones because the impact of a neutron, having as a outcome fissile some a little bit lighter elements and more neutrons that are the ones that can make this chain reaction possible. In fission, the fuel is this uranium and plutonium, so we all know that the problems associated to the handling and so of these kind of materials. In fusion, what we have is isotope of hydrogen. I don't want to cheat. Tritium is also radioactive, but has a lifetime of 12.5 years, so it's much different from any uranium and plutonium and so. Also, in fission, you have high-level rad waste. In fusion, you have low-level rad waste. It's not true there is not production of rad waste. This is something that we need to understand. But it is very true that the level of radioactivity in fusion and fusion is completely different. In fusion, you don't get more than low-level rad waste. In fusion, you have these transuranic elements, and so you end up having really high-level rad waste. One good feature of fusion and of fission related to fusion is a reality. There are now fission power plants that are working and producing energy to the grid. Fusion is still under development, and let's hope to have this new source of energy soon. But as I said, it's still to be proven, to be done on Earth by human beings. So how can we produce that energy on Earth? Because we have seen it's a natural process, it's the one power in the stars. we need to have this plasma, as I mentioned before, and we need to reach very high temperatures to provoke the high energy collision of the nucleus and have these reactions. We need to have enough density to increase the probability of these collisions to occur. And this has to be done for long enough time to be able to have enough fusion reactions. So this high temperature, particle density, and confinement time is known as a triple product. So these three magnitudes has to reach, the multiplication of these three magnitudes has to reach certain threshold to be able to have fusion. If we don't have this, if we don't reach that, we don't have fusion in a machine. So as you can see, you have to fulfill these three requirements in a way that they compensate each other to be able to have fusion. If this is not true, the fusion reaction stops. This is why it's so difficult to have it, and this is why it's very safe, because unless you really reach the conditions, you don't have fusion in your machine. So there are a number of reactions, of fusion reactions that can happen. The easiest from the energetic point of view, the one that is produce a lower temperature and so is the deuterium tritium, and is the one that is widely pursued here on Earth to take place. ITER machine is based on that reaction, and many of the other machines linked to the private sector is also based in that reaction. The deuterium reaction that you have here in this slide, also highlighted, is the one that is producing the sun. It's less efficient than the deuterium tritium, and this is one of the reasons why the sun will be shining for longer, because this reaction is less efficient. Otherwise, the lifetime of the sun will be shortened if there will be deuterium tritium. So how far are we of having this condition of having what we call reactor condition by using this triple product? So you can see here how the technology has been improving. All these names, for those who are not familiar, are fusion machines names, mostly tokamaks. And ITER, which is under construction in France, is the machine which is getting closer to reactor condition, but not even yet. Why? Because ITER is still an experiment. And to be in reactor condition, we will need to go beyond ITER. We will need to go to a demo machine, a prototype machine. And when you get this reactor condition, it's called ignition. Ignition means that you have a fusion reaction, the deuterium tritium reaction, for example, and you are able to keep the reaction self-heating. So you don't need to add extra power into your machine. And this is achieved when you have the level of fusion, that fusion reactions produced in your plasma high enough where all these helium particles are able to self-heat the whole plasma and keep the reaction going. To achieve that is ignition. And that was proven first time to be done on Earth only a few months ago by Livermore National Lab in an inertial fusion machine. So until 2 or 3 months ago, that was not reached on Earth. So I don't have too much time, so I want to give you a brief overview of the different concepts. Fusion is still under development. As I told you before, we have not yet a machine producing fusion energy and put it in the grid, so a number of different approaches are pursued. The gravity is the one that the sun is using, so we cannot replicate it on Earth. It's just for reference. This is how the sun confines the particles thanks to gravity, but we need to do it on Earth by using other methods, usually magnetic fields. You have the approach of inertial fusion where lasers heat up a target to reach this high temperature and then the implosion and so. Then you have the magnetic confinement, which is the most popular approach. It's not the only one, but it's the most popular, when you have a toroidal machine where magnets produce these magnetic fields to confine the charged particles, and you create currents inside, and then makes the whole density of the plasma to increase because you have this double confinement in the case of the tokamak, and then you can reach these conditions, but there are a number of different approaches. You have in the part of the inertial fusion, which has also some military application, as you can see here. You have open-edge system, magnetic mirrors and pinch and multiples. You can Google it and see how they work. It's whole family. And then you have the closest system, this toroidal machine mostly, where you have accelerators and tokamak, as I say, is the most popular one. 90% of the machines proposed right now are based on tokamak designs. So this is how it looks like, the interior of that machine. This is a tokamak, and on the right you have the accelerator. The biggest tokamak being built on today on Earth is ITER. The biggest accelerator is Weldstein 7X, as is in Germany. You can see here a whole picture of the ITER plant, and this is how the ITER machine looks like from inside. This expected, the first plasma was expected by 2030, maybe a little bit later. And the ITER colleagues say that they intend to keep the full nuclear fusion by 2035. They are now revisiting the plans and so, but let's say in the 30s. It's an international project. You have 35 partners, and they are all working together to be able to put in place this machine. It's a technological challenge, a coordination challenge, a logistic challenge, a challenge in all aspects. But the project is moving, and I'm really confident that it will produce much more than is on papers, let's say, today. So what is beyond ITER? Because now you have an explosion of new concepts, new enterprises, new prototypes, and people promising fusion in a few years, which is good for the whole community. The first thing that we need to understand is ITER is an experiment. ITER will not generate any megawatt to the grid. That needs to be done by the next step. It's a demo or prototype or whatever you want to call it. The next machine will have to produce some megawatts of electricity to the grid, and it has to operate in a closed fuel cycle. That means that the tritium that you need to fuel the machine needs to be produced into the machine by a breeding process with lithium. So these two things are not going to be done in ITER. This needs to be proved by a demo prototype machine. And there are an European demo, that there is a project that they are working on that, but in addition to that, there are a number of private enterprises. They are all aiming for building this demo or prototype or whatever you want to call it, with different approaches, some of them more standard like a tokamak, other more challenging like helium or sub-energy and so. But all of them feature some good characteristic of fusion, and they are making progress in the different concepts. Let's see how it evolves. It's a really interesting time for fusion. So just a couple of words on women in fusion. We created a group a couple of years ago to give visibility to fusion, to the role of women in fusion, and to push for having an international network of women in fusion, because fusion has been international since ever. So a group of friends, here you have the picture of us, decide to get together and do something. And after a lot of discussion, we say, okay, let's create this global group. We want to be the platform of everyone who has something to say related to the role of women in fusion, to offering mentoring, to provide the chance to have networking, etc. And we want, again, our aim is to be a global platform. So whatever event that you can do, whatever thing that you want to promote, contact us and we will do it from our website and through our all resources. So we have a global presence. We have more than 600 members. And if you want to join, it's for free. You only need to get the website and say join, and you join. And we are offering also a mentoring program that we have as April 12 mentors, or 11 mentors and 12 mentees. So I don't want to put much more time on that. Just go to the website. Here is the contact information. If not, you can always send me an email and read, go through, and if you like it, join to the group. So back to the conclusion of the whole talk is fusion energy is becoming a reality, and fusion needs all the talents to become a reality. So I'm really encouraging all young people and not so young people to join fusion, to get interested in fusion and contribute to this new source of energy. So, and that's all.
Thank you.
Questions? So
Sehila. We keep it open for the question and answer sessions. Thanks for a very nice and interesting talk on fusion. Any
Yeah.
questions?
Yeah,
I have raised my hand.
can I ask you a question, Dr. Sehila?
please.
Yes, I think the National Ignition Facility has achieved break-even, isn't it? So that's what I mean, I'm told. And I spent almost 40 years in the field of high-power lasers and fusion. I mean, I keep getting the news. And yesterday we had a lecture from the Laboratory for Laser Energetics from Rochester. And I think the National Ignition Facility has reached the scientific break-even, that is, right?
Yes, the National Ignition Facility it was the very first time that it was proved that thanks to a fusion reaction that took place, the energy that reached the target was lower than the energy that it was produced. So it's breakthrough is having the proof of having a burning plasma and being able to prove that the energy that you put into the system, it was less than the energy that you produce. So somehow you validated the whole fusion scheme. Said that, it's not true that the energy, the Q of the whole system was larger than 1, because that took into account the energy that was put into the target, not the energy that was put into the lasers, okay? Because there were losses over this way until to reach the target. But it is true if you focus on the fusion part, so you say the energy that I was managing to put into the target and the energy that I extracted from the target, the energy extracted was higher. And that is a really important step for fusion.
Oh, very interesting. Yeah, we have still a long way to go. And my second question is, having spent so many years in fusion, I mean, it has become a part and parcel of my life, I would say. 40 years working at BARC on starting from the scratch, making even several joules laser, kilojoule laser, and things like that. Is it possible for me to join the team of women in fusion?
Well, this is my fault that I didn't explain properly. Women in
Yeah.
Fusion is open to everyone who
Yes.
pursues fusion, who is a fan of fusion, who is connected to fusion to some degree. So please, you are very welcome. You and your colleagues, you are really welcome to join Women in Fusion.
Thank you. Yes, I will write to you. Yes.
Hello,
Thank
can
you.
I ask a question? This is Rohini Godbole. Hello,
Yes, I can hear you.
can I ask a question? I'm asking the chair.
Yeah. Please go ahead and
Thank
ask.
you.
Rohini.
Thank you. First, let me thank you for a very interesting talk. And the earlier person already asked the most important question about lasers because that was her expertise, but that was going to be my one question. But now I'm going to ask you a slightly different question, more related to your women in fusion exercise that you talked about. So I know, I mean, I'm a particle physicist, so I have a lot of experience of lot of Spanish colleagues. Spanish and Italian women are much more in number than let's say German or Austrian. Now, given the fact that you have been involved in KIT from what I heard, and also IAEA, I wanted to ask you whether there is any the kind of women in fusion exercise that you have started. Is there a multi-country exercise about a pan-European exercise of women in physics, apart from, from these lines? Are you
Well-
member of any such effort? I just wanted to know.
I know, and because we are in contact with them, there are a group of women in physics led by some Spanish colleagues and Spanish. So
In Spain,
uh,
yes.
yes.
There is a IUPAP effort which puts together women in physics from all over the world. But
Yes,
I
we
was
are-
wondering whether, particularly because you're working in, you have experience in Germany and Austria, I was wondering whether these countries have any effort like what you are right now talking about in Women in Fusion.
Well, I can tell you that I'm aware about this women in physics, and we are in contact and so on. So I don't know any particular group in Germany or in Austria. Women, I want to make it very clear, Women in Fusion is a global group. It's not a national group or European group. We have Americans, we have Europeans, and we have people from different institutions. So it's a full global. We wanted to make it global from the very beginning. And I don't know any particular group in Germany or Austria. I know this group of women in plasma physics, which is run by the Spanish colleagues. So
Okay, no, thanks, because one is always thinking, that was also a second very important message from your talk. And I for
No.
one also believe that this kind of getting together of the groups in a particular areas like technology and physics, chemistry, maths, where there are not so many women, it's sort of very important. So thanks to you as also the previous speaker for talking about, important technological contributions. And thanks again. Best wishes.
Good morning, ma'am. I have few questions to ask you, ma'am. You said fusion will give to low-level liquid waste, low-level waste. No, what will be the state of the waste, like solid, liquid, or plasma, and what is the plan to manage that low-level waste generated by fusion reaction? And I have one more question also. The second question is, you said the fully functional fusion reactor will be operational by 2035, no? Which will be the country in which it will be first operational, first fusion reactor, where, or it will like in a ITR facility? I just wanted to know, ma'am.
Sure. Thanks very much for the question about the rat waste management. How is fusion right now envisioning that thing? But the first answer is how ITER, which is the first machine being built and the first one having plans for how to handle with the rat waste, is to go to deposits, repository places, and that's all. We are now pushing, in particular in Clean Air Task Force and in other places, for starting a strong R&D program in recycling. If we are able to recycle as much as possible of this low-level rat waste, I think it could be a really good message for the mankind to try to be as clean as possible. And also it will be a really good feature of the industry. So right now it's low-level rat waste, and the point is to go to a deposit, a repository, and that's all. Can we do something else? Yes. Can we can try to have some recycling, and we aim for that. This is answering the first question. The second question about when the fusion machine will be in operation, I probably explained myself wrong. What I say in 2035 was related to ITER, when they expect ITER to be in the in the nuclear phase. It was an estimation of a couple of years. Now this date is under revision, but these are the dates of ITER. ITER is a single machine and it's an experiment. If you go now to Google and you start to find all the announcements done by a number of different private enterprises, the other day Helion said that they were going to power on that data center from Microsoft in 2029, if I remember correctly, so in a few years from now. You can go to another enterprises and they say they are going to put energy to the grid in the 30s. So this is unknown. We are now in the race to see who